before I get started, I'd like to give my acknowledgments. First of all, Dr. Hain, you've been lovely, told us a lot. I always wanted to read it yesterday in senior design. Thank God I finally got it. Next, the man behind the scenes, Mr. Knapp. Every time I come into his office sweaty, crying, really wanting to give up. He assured me every time, give me all the parts I needed. You guys have been great. You really helped us out. My name is Douglas Davis. I'm a cadet here. Do my thing. I'm with All-in-One. My name's Adam Gullis. Greg Hart. Joseph Sheen. Today we'll be showing you our product, the Powers Edible. First of all, I'll go over an overview. Basically, what is the All-in-One? What's this thing everybody's been talking about lately? This All-in-One. Tonight you'll find out. Building the All-in-One. What actually went into it? The hardware we used, the software we used, and the actual applications that came into play into building the device. Finally, we have the budget analysis, how much everything cost, if we stayed in budget, if we were out of budget, what actually worked, and our conclusion, what we learned, the things that we actually took away from the project, things that were important, and we'll have some time, if we have time, for questions and answers. I know everybody wants to get to that refreshment table, it's right on the corner, literally and figuratively. So, first of all, the problem. Modern day society revolves around two concepts, punctuality and convenience. First of all, we want to be on time for all of our occasions. We want to actually have the time right. Also, we're pretty lazy. I don't like doing hard things. I want a machine that will do most of the things for me. Second of all, have you ever actually tried to program an alarm clock? It's pretty difficult, right? I like to imagine an analogy, sweet old grandma. She's sitting there, she's clicking the minutes button. Just keeps going past the one that she wants. With the All-in-One, all these problems are solved. But, like I said, what is the All-in-One? Basically, the All-in-One, before I get to these things, it's a Bluetooth-enabled device that can do three basic things. Users are allowed to input either time, text, or alarm messages. You can either set the time, which will be in military time. You can either set an alarm, so when the time eventually gets to that time, the alarm will go off. Or, this is what sets our product apart from any other alarm clock, you can actually set in personalized messages to scroll across the screen. All of this is done through a mobile app, an Android app. Basically, we'll get to it. Next, Bluetooth-enabled device. It's an LED alarm clock. Like I said, you can have personalized message displays, and it's Android smartphone compatible. We couldn't really use iPhones because Android is actually open source. It's pretty hard to program things with an iPhone, so that's why we picked it. Now we get to building the All-in-One. We'll be going over the hardware used, the software used, the Android application, and with the microcontroller that we use, the PIC-18, and the application that went into it. First of all, the PIC-18, why we picked it. Mainly because we actually knew how to use it. A lot of teams use things like the Arduino. I didn't want to deal with that. We actually knew how to use assembly language. We'll stick to what we know. That's the main reason that we picked that PIC-18. Other reasons are it was actually able to drive the LEDs and speakers that we were using, and it was able to time multiplex. Then the next slide, for those of you that don't know that, I'm pretty sure everybody knows what that is right now. But I'll explain what time multiplex is. Now, the display for the All-in-One is actually 4 8x8 LED displays, and they're put together in series. So it's actually a 32x8 display. And basically, to achieve the image on these displays, we are doing something called time multiplexing. What I've tried to explain to people whenever I try to go over my project with my clients, I try to get them to understand that when you see these LED displays, it's not actually every LED lit up at once. In actuality, it's one column lit up at a time, then the next, then the next, then the next. What's happening is known as precision of vision. What you're actually seeing is them all getting lit up so fast that your eyes are perceiving that they're all actually on at the same time. Pretty neat, right? Next, I'll turn it over to my teammate, Adam Goss, to explain the digital receiver.
Alright, so Davis already discussed a little bit about the Bluetooth that we're going to be using. We're going to be using the Android application on our phone. This is digital receiver that we're using to talk to the Android application. It's an Arduino wireless Bluetooth serial transceiver. The firmware that's on this is actually called the HC06. As you can see, it's got 4 pins here. The first one's for powering it, the second one is for the ground, and the other 2 pins are for send and receive. We won't actually be using the receive pin because we're actually trying to transmit the data to the microcontroller. even though we're receiving data from the application, we're trying to transmit that serially to the microcontroller. So it actually is PIC-18 compatible, even though it is an Arduino device. So PIC-18 compatible means we both have them set up to baud rates of 9600, and we have transmit set up to one port to be able to read from the microcontroller.
Next, we'll turn it over to Credit Card to explain the gates that we use and the heat.
All right, so because we have all our devices splitting up, we can't just have one power supply for it and have proper power allocation going on. So we had to use buffers. When we stuck our hands into the box components, one of the first ones we grabbed was the NOR gates. So that's what we ended up using. Unfortunately, had the problem we didn't realize immediately that we're going to have to do the opposite of what we wanted to in order to light up the LEDs. So that caused a little bit difficulty with programming, but we made it work out. So we use this to be able to properly light up our LEDs and make sure power goes through. Another device that we had to use was decoders. You only had so many outputs on the microcontroller, and we had to light up a whole lot of LED matrices. As you saw earlier, all the pin outs for that. You had 8 coming in for the cathode, 8 for the anodes. So you required decoders to be able to reduce the amount of output bits.
Next, we come to the power supply. In our seed paper, it actually says an 8-volt, 200 milliamp power supply. It was just recently that we actually switched over to a 5-volt power supply. We were having a little bit of trouble with voltage regulators, so in actuality, using a 5-volt that we were able to find, Mr. Knapp, was a lot better choice. Simplicity is key to the thing. Attached to that is a reverse bias diode that allows, basically, we don't want to short out any of our devices. We don't want to plug this thing and catch something on fire or destroy something, so that's why that's in use. And a capacitor is also placed in parallel to get a steady voltage going into the device. The software we used was the Android SDK with Eclipse IDE programmed in Java. I have to give kudos to my boy here, Adam Goss. No one knew how to program in Java, which makes writing an app pretty difficult. So he did a very good job getting the app together. We also used MPLAB X IDE version 1.85. That's how we've actually programmed the PIC-18, how we've been doing our field testing. And something that's actually come in handy for the past couple of weeks was the PIC-18 simulator that we used in 330 with the programmable microwave. That's been very useful in troubleshooting. And I'll hand it back over to Adam Goss to discuss the application.
Alright, so we already discussed a little bit about the application. We compiled the application to operate between API level 11 and API level 19. So this gives us a range of about phones from early 2011 to about, well actually, modern phones now. So it's easy to start and operate. As soon as you click the icon, it should pop up the application. There should be no calibrations needed after that. And we've tested it, even though we already know that both of the devices are Class 2 Bluetooth, and they have a range of about 30 feet. We have tested it, and we do get reliable data transfer at up to 30 feet. And so this is the meat of the matter. This is how it looks. As you can see, it has buttons, everything. When you first start the program, there actually will be a prompt for you to connect to Bluetooth. And once you connect to Bluetooth, then you'll be able to go to this screen. If you don't connect to Bluetooth and you click no, it'll turn you out of the program and you'll have to start it up again. By the time you click yes, you can see up here, I don't know if you can read it from there, but it says you aren't connected to the all-in-one, which means we haven't connected yet. So you need to search for your device up there, and once you search for it, you can see the list of devices closest to you. The one we actually have is called the HC06, and that will connect to the all-in-one. Once you're connected, you can then send your custom text, time, alarm. You load them up into that field. Military time, military alarms. Text, we limited that to 35 characters because Barton really likes Snapchat. And click the button, it'll send it. We'll talk a little bit more about how you read it later. The stop scroll is for whenever we're actually scrolling time. We can stop that by sending a flag to tell it to stop. And then we put a big analog clock and a digital clock with the current time in the middle, just in case you can't read the one up in the top right corner. chart. Start the program, initialize, you enter your data, it asks you to time, text, or alarm. And once it deciphers between that, then it appends the flag that we're going to be using to register that in the microcontroller, and it goes through the Bluetooth routine and then sends it back to this loop right here. This is what it kind of looks like in the file registers of the PIC-18. I don't know if you guys can read that right there. That's an A3. That's the flag we're using for text in the red there. And that's the first flag that the microcontroller will actually see, so that it can decipher that it's text. And then you've got your data bytes loaded up. This is the whole meat and matter. Then the green here, you can actually see the ASCII for it. It says flags all right in caps. And then at the bottom here, you can see in blue, that's our end return byte. That tells the microcontroller that we are done with this string, and that's the end of the string.
The PIC-18 application, basically it uses assembly language, like I said. It will actually decipher inputs, and it will use subroutines/interrupts for letter recognition in time. As he stated in the last slide for one of the interrupts, it actually started out with an A3. The way that we're deciphering through these interrupts, text will have an A3 at the beginning, time will have an A2, and alarms will have an A1. That's the way that basically a file select register is reading through every one of these bytes. The very first byte is what differentiates each of these lines of data from each other. So that's how we're actually going to be able to decide if a time is being displayed or if the alarm is being set, vice versa. Here's a simple flowchart of the main program for the PIC-18. I'll go over the interrupts used within the PIC-18 as well. Basically, once it powers on, inputs are initialized, and then it's constantly asking our inputs being received. Is that A3, that A2, or A1 been received in the message? And once it has been received, it'll go on to the proper subroutine to actually load the proper output of the display or to scroll a message across the screen. The interrupt vectors that we use, timer 0 is actually used to count 1 second intervals. Basically, every second will be counted. We have a counter counting up to 60. Once 60 has been reached, they'll start counting up minutes. Once those minutes have been reached, they'll start counting up hours. It's just so on and so forth. These counters building on each other that allows us to actually keep time. The timer 1, that's used as a millisecond counter. That's actually what we're using to achieve time multiplexing. Every millisecond, a different column of the all-in-one is being lit up. And that's actually what's controlling the differentiating between each column to turn them on one after the other. And the RCIF flag, which Gus could probably better explain.
Alright, so I talked a little bit about the flags it's actually going to be used, but the RCIF flag is an interrupt flag in the microcontroller. So we keep checking this in our main subroutine. Our main subroutine to check and see if it's set. If it is set, that means there's something in the RC ring. We move that out, load it, and we load all that into a table, including our flags on the end of the bottom. And every time you check that flag, it clears it.
Now for the best part. I love to make some money, I love to save money at the same time. With the, we're using a simple 8x8, of course, LED matrix 4 for the all-in-one. I always was taught by my professor, keep it simple. With a little extra word on the end, but keep it simple. We don't need a high definition display. We need to show the basic numbers and letters of text and time. For now, we're using, like we said, the PIC-18, $75. We want to, later on, when it moves on, strip most of the components of the PIC-18 so we can reduce the price a bit. The Arduino transceivers, we bought 2 for the time being for one test in case we broke it. We had another one to use. We have lots provided to us already. And the very first picture you saw was the code box. So that's going to hold the all-in-one, all the components of the all-in-one, and about $65. In the end, it'll be about $170. But by the time it's refined, the all-in-one probably costs about $50 for the consumer.
In summary, what is the all-in-one? Perfect system, right? You can put pretty much anything you want into it. Get the displays, put anything you want. Building the all-in-one, we went over the hardware, the software we used, and the programs that went into the building. For our budget analysis, we came up to a budget of about $172, which is well under the range of what we were allocated. And what we didn't discuss so far was some possible use of the all-in-one. So I'd like to give you all a couple of examples that are things that I always came up with. First of all, last summer, I was always looking for my boss at my internship. Never could seem to find him. If only he had an all-in-one sitting on his desk that he could say, out to lunch, turn around. I wouldn't know. Another great use that a mother actually gave me was, what if I can't wake my kids up? I'm downstairs making breakfast, slaving away. I want to wake them up. I can set an alarm from my kitchen. I can also put across the screen, pancakes are ready. And of course, conclusions. The implementation of each of the components of the all-in-one, the simply used Bluetooth device was the key. Though the end product has a very simplistic use of time, alarms, and scrolling notifications, it can be inferred that bigger and better things can eventually be achieved through the use of Bluetooth. It is my hope and desire that we are stepping towards the home of tomorrow. Soon, everything in your house will be used through a Bluetooth device. You won't ever have to leave the house. And then, of course, questions. Anybody?
During when you had the blueprint set up, who had the nice nails? Was there a picture of you guys?
Not bad, but
Should have known.
On the visual persistence in it, you got a 32 by 8 display, and you're stepping through it 1 millisecond, so you're going 32 milliseconds, and then so that's roughly 30 frames per second. Is that where you need to be on that?
Right now we're actually troubleshooting the display. That's the last thing that it's actually coming in a little bit hazy. So in all honesty, we might have to step up the time a little bit.
Can you do that? Because it seems to be you're right at the edge there.